Everyone. I'm honored to introduce the paper Unleashing the Potential of Vision Language Models for Long-Tail Visual Recognition to you. I'm Te Ma from Shanghai Artificial Intelligence Laboratory. I will introduce our work from four aspects: background, Bayesian method, the TAGO method, and the results of the models. Deep models can be largely attributed to the availability of large-scale and high-quality datasets like the ImageNet, the MS COCO, or the Connectis 400. However, the data imbalance has inevitably emerged since the real-world data often abide by a long-tailed distribution. Due to the imbalanced data, the long-tailed visual recognition methods are needed to tackle the data problem. A research field seeking robust models that are resistant to the significant imbalanced class distribution and can deal with the future learning of the tail classes. About the previous long-tailed models, they can be split into two kinds, and the first one is focused mainly on class rebalancing the strategies, like reweighting the categories of the long-tailed classes, and the second one is improving the network modules, like the classifier designing or the representation learning. However, these methods entirely rely on the visual modality, but in this paper, we raise the question whether language modality can be effective and complementary information for the long-tailed recognition task. Therefore, we introduce the balanced linear adapter method, which can be abbreviated as the BALAD for you. In phase A, we keep training the visual and language branches of the pre-trained vision language model such as CLIP simultaneously. We use both the vision-to-language and language-to-vision contrastive rules as the training objective. Then, in phase B, we freeze the vision-language backbone obtained from phase A and utilize an additional linear adapter layer to help our model refine its visual and language representation on those tail classes. The additional linear adapter layer is used to adapt the visual representation and combine the original visual features with adapted ones. As shown in the left figure in the orange box, both the linguistic and the visual encoders are fine-tuned based on CLIP on the long-tailed datasets, and in the blue box, the fine-tuned vision language model is frozen and only a linear adapter is fine-tuned. This kind of decoupled fine-tuning is better than joint fine-tuning, as can be observed in the TSNE visualization figures on the right. There are clearly boundaries between the similar classes. However, there are limitations of the BALAD method. First is the heavy computational overhead of fine-tuning. The quadratic complexity of the transformer brings about huge fine-tuning computational cost, especially when meeting the fine-grained dataset like iNaturalist. The linguistic encoder will be hard to fine-tune as the sequence of token is too long. Moreover, the choices of backbone is limited. We should choose CLIP visual backbones to fine-tune. We propose a non-parametric retrieval strategy to convert conceptual knowledge from visual linguistic pre-trained weights into images, named as TACO, meaning transfer conceptual knowledge from language to image. Based on unannotated web datasets, conceptual 3 million and conceptual 12 million, SBU caption the photo dataset. Then we retrieve images from web data memory according to the cosine similarity of web images and target categories. The retrieved images are combined with target dataset to compensate for the data insufficiency, especially for tail classes. Note that only the parameters of downstream visual encoders are updated during the whole process, and the visual encoder can be anyone you like. For example, ResNet, Vision Transformer, or any others. Tackle can transfer the conceptual knowledge without fine-tuning, as the retrieved images complement the target datasets from various perspectives. For example, the cartoon, the mockup, and design diagram as shown in the figure. We conduct our experiments on three long-tailed benchmark datasets, namely ImageNet LT, Places LT, and iNaturalist 2018. The ImageNet LT and Places LT are modified from the normal ImageNet and Places 365 datasets, while the iNaturalist 2018 is a real-world long-tailed dataset. It can be seen our Ballard and the Tackle models achieve SOTA performance with various backbones on all three datasets. The Ballard performs best considering the huge computational overheads, but the Tackle also shows excellent performance with only training the visual backbones. From the zero-shot performance comparison, the results are largely improved compared with zero-shot results, were especially obvious in fine-grained datasets like iNaturalist.